Hello, let's start with two examples from the last week. There are two examples from the 2 degree of freedom systems. Okay, the first example, we want to find the force vibration response of the system shown below when F1 is a step force of magnitude 5 Newton using the Laplace transform method. As I explained, when the external force is not harmonic, we need to use the Laplace transform method for 2 degree of freedom systems, similar to the single degree of freedom systems. And here in this case, we have the zero initial condition. As you can see, x1 at t is equal to 0 is equal to v naught, v1 at t is equal to 0 is equal to 0, and x2 and v2 at t is equal to 0 is 0. So the initial conditions for this problem is 0. The mass m is 1 kilogram and the stiffness of the spring is 100 newton per meter. There are 3 springs and we have 2 masses, so the degree of freedoms here considered x1 and x2. So the first step, we need to extract the equation of motion. For this purpose, we can write the Newton's second law for each mass separately. For the first mass m, if we assume that mass m is going down, we will have one force due to this spring in upward direction, and it's equal to k times by x1. And also we will have another force in upward direction due to the spring between the two masses, and the force is equal to k times by, here this spring, the both edges of these springs are moving. One edge, this point is moving by x1, and the other edge, the lower edge, is moving by x2. So k is equal to the force is equal to k times by x1 minus x2 or x2 minus x1, and it depends on the direction of this force. According to this direction, in upward direction, this force is equal to k times by x1 minus x2. And if you want to put the reaction of this force on the lower mass and this mass, it must be in downward direction, and it's equal to k times by x1 minus x2. But for the free body diagram for the second mass, we assume that it's in upward direction, so it must be multiplied by 1 negative, and it will be k x2 minus x1. So the sign of x2 and x1 depends on the direction of the force. And finally, we have one force here due to the lower spring, and it's equal to k times by x2. In this problem and in this example, in the free body diagram, we do not consider the weights, and this is because we have some initial deflection in the springs due to the weight of these two masses, and we can neglect the weight and also neglect the initial deflection in the equation of motion. So if you write the force equation for the first mass and second mass, you can extract two equations. The first equation, this one, will be extracted from the Newton's second law of the upper mass. We will have one force k x1 plus k x1 k times by x1 minus x2, and minus f1 is equal to minus m x double dot, or we can multiply by 1 negative and simplify this, and you can extract the first equation. The summation of the force is equal to mx1 double dot. And for the second mass, the lower one, you can write again the Newton's second law, the force equation in vertical direction. The summation of the force is equal to minus k x2 and minus k multiplied by x2 minus x1. It must be equal to by mx2 double dot. So this is the second equation. And now we can simplify these two equations and write them into matrix form and obtain the response. Here in this case, because f1t is not a harmonic function and this is a step function with amplitude 5, we need to use the Laplace transform method, and we can now write the Laplace transform of these two equations. The first equations, we have m times by x1 double dot. Because the initial conditions are 0, so the Laplace transform of x1 double dot is s squared times by uppercase x1s, which uppercase x1s is the Laplace transform of lowercase x1. I mean the Laplace transform of, this is our assumption, that x1 in time domain is equal to uppercase x1 in Laplace domain. So this is the Laplace transform of x1. So x1 double dot Laplace transform is s squared times by uppercase x sub 1. And here the Laplace transform of x1t is again x1, and the Laplace transform of x2 with the same procedure is uppercase x2s in Laplace domain. The Laplace transform of f1t, we assume that is f1s, and you know that the Laplace transform of a step function is 1 divided by s, but here because the amplitude is 5, so f1s is equal to 5 divided by s. Now we can simplify these two equations, and for the second equation you can do the same procedure and extract the Laplace transform, as you can see. And now we need to solve these two equations, these two algebraic equations, and obtain x1 and x2 from these two equations. You can use different methods. You can write it in the matrix form, and then x1 x2 is equal to the inverse of the matrix of coefficients multiplied by this vector, the vector of fs, which is 5 divided by s and 0. This is the vector of a non-homogeneous term, or fs. Or you can directly solve the first equation. For example, from the second equation you can obtain a relation between x1 and x2. You can obtain that x2 is equal to k divided by this term, which is m s squared plus 2k multiplied by x1. So here you can substitute in the first equation. From this term you can substitute, instead of x2 here you can substitute k divided by ms squared plus 2k times by x1, and then you will have one equation in terms of x1, and you can solve it for x1 and obtain it. And also you can substitute the numerical value for m and k and then solve them and obtain x1 and x2. Anyway, you can solve this system of algebraic equations and obtain x1 and x2. And here you can see this is x1 and x2. And the next step, we need to find the Laplace inverse of x1 and x2 to obtain the response in time domain. But to find x1 and x2, you need to calculate a1 to a5 and b1 to b5, which are the coefficients. For this purpose, we can write x1, which is a fraction, as you can see, in terms of 3 subfractions. Here, a1, a2 to a5 can be obtained from this equation, and also for b1 to b5, again, we can solve them. You know that the numerator of the equation in the right hand side must be equal to the numerator in the equation in the left hand side. So a1 multiplied by the denominator of the second and third equation plus the numerator of the second equation multiplied by denominator of the first and third equation plus the numerator of the third fraction multiplied by the denominator of the first and second equation must be equal to the numerator of the equation in the left hand side. And for x2, we have the same procedure, and you can obtain three equations for, five equations for a1 to a5, and five equations for b1 to b5 for each of the responses in Laplace domain. And then you can solve these five equations for five unknowns and obtain a1 to a5. Here, from the first equation x1, you can see that we in the left hand side we have 5s squared plus 1000. Here you can see this term, and in the right hand side we have this term multiplied by s to the power of 4, this term multiplied by s cubed, this term multiplied by s squared, and finally this term multiplied by s plus a constant coefficient 30,000 multiplied by a1. So the coefficient of s cubed, and s to the power of 4 must be equal to 0, because in the right hand side of this equation, there is no s cubed or s, and only we have s squared and a constant term. So the constant term, it must be equal to 30,000 times by a1. So from here you can conclude that a1 is equal to 1000 divided by 30,000. The coefficient of s squared, this term must be equal to 5, and other coefficients, as I told you, must be equal to 0. So we will have five equations. We can solve them for a1 to a5. For b, the second equation, again we have the same scenario, but this time in this equation, the right hand side, there is no s, so all of the coefficients of s to s squared, s cubed, and s to the power of 4, all of them must be equal to 0. All of these terms must be 0, and only this term is equal to 500. Now again we have five equations with five unknowns, and we can solve them. As you can see, these are five equations with five unknowns, two sets of five equations, and then when you solve them you can obtain x1 and x2 in terms of these subfractions. And now we can use the Laplace transform, and inverse Laplace transform, and obtain the response in time domain. Of course, here you should refer to the table that I used in the single degree of freedom systems. You can use the table, but here just to remind you that the Laplace transform of sine at divided by a is equal to 1 divided by s squared plus a squared. So the inverse Laplace of the terms, of course here all of the subfractions has s in the numerator, as you can see. So the inverse Laplace transform of all of them is cosine in time domain, as if you use the second note here, the Laplace transform of cosine is s divided by s squared plus a squared. So the inverse Laplace of all of these terms is cosine in time domain, and for this one the Laplace transform is a unit a step function, okay, of course with this coefficient. So you can use the inverse Laplace to obtain the response in time domain. I guess the main challenge for you in this type of problems is to obtain these coefficients, the coefficients for the numerators in the subfractions. Okay, any question from this example? Is it clear?
Yes, sir.
Okay. Okay, the next example, here we have a system without any external force. We want to find the response of this system with these numerical values subjected to an initial condition. According to the initial condition, the initial velocities are 0, but the initial displacement for x1 and x2 are 0.05 and 0.1 respectively. So we can extract the equation of motion, and again we want to use the Laplace transform. So to extract the equation of motion easily using the Newton's second law, you can write the equation of motion for this system, and you can find the Laplace transform of these equations. As you can see, this time, because the initial condition are not zero, in the previous example these initial conditions was zero, so we neglect all of these terms, and easily we wrote, instead of x1 double dot in Laplace domain we wrote s squared x1, or instead of x2 double dot we wrote s squared x2. But this time these initial conditions are not zero, only the velocities are zero, so this term is zero, this term is zero, but x1 and x2 are not zero, and we can substitute from the initial conditions, and then we can extract the system of algebraic equations in Laplace domain. Here you can see this is the system of algebraic equations, and if you substitute the numerical values, you can write it in this form, in this Laplace, the matrix form, and by using the inverse of this matrix of coefficient, you can find x1 and x2 in the Laplace domain. So x1 and x2 can be obtained, and now we can substitute for the numerical value for m2, k2, m1, and k1, and simplify these equations and obtain the subtraction similar to the previous example, and obtain the response by using the inverse Laplace in time domain. Okay, here in this slide you can see the numerical values for x1 and x2, and this is the x1 and x2 in Laplace domain. The next step, we can write them in the subtractions. As you can see, we will have two different subtractions according to the form of the denominator, and again we can find a1 to a4 by calculating these two equations. From this equation, the first numerator multiplied by the numerator of the second equation, and the numerator of the second subtraction multiplied by the denominator of the first subtraction must be equal to the numerator of the main equation. And for the x2 we have the same procedure, and we can obtain a1 to a4 with 4 algebraic equations and 4 unknowns. And finally, x1 and x2 can be obtained from the inverse Laplace and using the table to obtain the response in time domain. Okay, any question from these examples? I think with this example, we can wrap up the 2 degree of freedom systems and start the multi-degree of freedom systems. Any question? Is it clear?
Yes, clear.
Okay, for the exam, remember that in this type of problems in the exam, when you want to, for example, use to Laplace transform, each part has a specific mark. So if you calculate the response in a Laplace domain, you will at least get half of the marks. And then if you cannot calculate the subtractions and find the response in time domain by writing the response in Laplace domain, you will get at least half of the marks. So in the exam, if you don't know how to calculate the Laplace inverse, you can at least write the response in the Laplace domain to get at least a part of your mark, because each part has a specific marks. Okay, so let me share the next slide. Okay, in this week we will start the multi-degree of freedom systems. In the multi-degree of freedom system, we will use the Newton's second law to extract the equation of motion similar to the two degree of freedoms, and then we will obtain the potential and kinetic energy expressions in the matrix form, and we will introduce the Lagrange equation to derive the equation of motion, and you will see that this method is applicable for the system with 2 degree or 1 degree of freedom. I mean, by using the Lagrange equation, you can extract the equation of motion for even a STOF system in previous chapters. And then we will introduce the eigenvalue problem, and finally the free vibration of undamped systems for multi-degree freedom systems. To extract the equation of motion for MDF system, we will do the same as the 2 degree of freedoms, but if we want to introduce this method uh, in different steps, the first step will be set up the suitable coordinates. As I told you, in 2 degree of freedom systems, first we need to obtain the coordinates, because you know that in the system with multi-degree of freedoms we can use different sets of the degree of freedom or coordinates. So the first step is to consider the suitable coordinates to describe the motion of your system. The second step, we need to determine the static equilibrium conditions, especially when you deal with a system in vertical position. Definitely we will have some initial deflection in the springs, so we need to obtain the equilibrium position. And finally we can measure the displacement and according to our coordinates with respect to the equilibrium condition. The next step, we need to plot the free body diagram, and finally by using the Newton's second law and writing the force or moment equation, we can extract the equation of motion for the system. Based on the number of the degree of freedoms, we will have a different number of the equations of motion, as I explained in the 2 degree of freedom systems. When we deal with a, for example, n degree of freedom system, we will have n equations of motion, and consequently we will have n natural frequencies and n mode shapes. So the number of the natural frequencies and the number of the mode shapes for your system depends on the degree of freedom, and they are equal to the number of the degree of freedom in your system. So here in multi-degree of freedom system, we will have multi-equations and multi-natural frequencies and mode shapes. Okay, for the first example here, we will have a system with 3 degree of freedom. As you can see, this is the simplest form of a system with 3 degree of freedom, with 3 masses and 3 springs. There is no damping. To obtain the equation of motion for this system, because this is a translational system, easily you can consider the coordinates as x1, x2, and x3. So this is the generalized coordinate system that we will use to extract the equation of motion. And this is the equilibrium condition. So now we can plot the free body diagram, and we can write the Newton's second law for each mass, and we must extract 3 equations for each mass. As you can see, for the first mass, the summation of the force must be equal to the m1 x1 double dot. This is for the first mass. Let me from the free body diagram of this mass. From the free body diagram of the second mass, you can extract the second equation, this one. And finally, from the free body diagram or for the third mass, we can extract the third equations. For the first one, if you write the force equation, we will have F1, because F1 and F2, both of them are in negative direction according to the direction of x1. So it will be minus F1 minus F2 is equal to M1 x1 double dot. F1 and is the force in the spring K1 and F2 is the force in the spring K2. The spring K2 has two movable edges. One edge moved by X1 and the other edge moves by X2. So the force in the spring K2 is equal to K2 times by X1 minus X2 or K2 times by X2 minus X1 according to the direction of the force. Here we assume that the direction is to the left. So the force in the spring K2 is equal to K2 times by X1 minus X2. And over here, for example, we assume that the direction is again to the left. So the force in this spring according to this direction is equal to K2 X2 minus X1. Okay. So we can write the force equation similar to the system with 2 degrees of freedoms. Here we can write the Newton's second law and extract the equation of motion, and then we can write the equation of motion in matrix form similar to the 2 degrees of freedoms and obtain the free vibration response for your system. Any questions so far? Is it clear?
Yes, sir, clear.
Okay, the potential energy and kinetic energy will be calculated similar to the single degree of freedom system, but this time we will have n mass, and in fact we will have n springs. To calculate the potential energy for the ice spring, we know that the potential energy is equal to half times by F times by X, which the F in the ice spring is equal to Kij times by Xj. And we can write the potential energy, the total potential energy, as a summation of the potential energy in each spring. So we can write it in this form, the summation of the potential energy in each spring, and finally we can write it in the matrix form, half times by X transpose times by the matrix of stiffness times by the vector X, which vector X is the vector of the displacement or the degree of freedoms, and in your case it will be the generalized coordinates that you will choose in the first step. The kinetic energy of the ice mass is also calculated half mixi dot squared, and the total kinetic energy is the summation of the kinetic energy in each mass, and finally we can write it in the matrix form, half x dot transpose, which x dot transpose is the transpose of the vector of the velocity, and x dot is the vector of the velocity, and this is the first derivative of the vector of your generalized coordinates with respect to time, and m is the matrix of the mass in your system. So this is the matrix form of the potential and kinetic energy, and you will see we can use them in the Lagrange equations. Okay, as I told you, Lagrange equation is a very useful method. In fact, this is based on the energy methods, and we use the Lagrange equation to extract the equation of motion for any discrete system with different degree of freedoms. I mean, it can be a single degree of freedom or multi-degree of freedoms. For this purpose, first we need to calculate the kinetic energy and the potential energy in your system. And then by substituting into this equation, which is called the Lagrange equation, we can obtain the equations of motion. If your system was a system with n degree of freedom, we will have n Lagrange equations and we can extract n equations of motion. In this equation, Q sub j is the generalized coordinates. This is obtained in the first step, as I told you. For example, in the previous example, Qj was x1, x2, and x3 when we dealt with a system with 3 degrees of freedoms. Q dot j is the velocity or the first derivative of qj with respect to time, and it is called the generalized velocity. Uppercase qj with superscript n is the non-conservative generalized force corresponding to the generalized coordinate qi. As you can see, this n means we will have n different non-conservative generalized force for each degree of freedom, and the force represented by qj superscript n may be damping or other external force. So according to these sentences, we will have the external force here, or in the Lagrange equations, the damping terms will appear here in this term in the qj, and j will be from 1 to n, and n is the degree of freedom in your system. So this n can be equal to 1. I mean, for a single degree of freedom system, you can use this equation, and instead of qj, we will have q, and q is the generalized coordinate. For example, when you deal with a simple translational system, q will be equal to x. And you will see in the examples when I will use this method, you can easily extract the equation of motion. And most of the time, we, similar to the dynamics, when in the dynamics you wanted to extract the equation of motion for a dynamic system, most of the time we prefer to use the energy methods, because the energy methods are will really decrease the difficulty level of your equations, and usually you don't need to consider, for example, in Newton's second law, in previous examples, when you wanted to write the force in the springs, you need to consider some assumptions to find the correct direction of the force. But here you will see in the Lagrange equation, you don't need to consider the directions, and easily you can calculate the kinetic and potential energy and substitute into this equation and extract the equation of motion easily without any assumption. And usually the Newton's second law will be more complicated than the energy methods. Okay, so you will see later in the examples that we most of the time prefer to use this equation to extract the equation of motion. Okay, if we assume that there are these forces F sub xk, F sub yk, and F sub zk represent the external force acting on the case mass of the system in the x, y, and z directions respectively, then the generalized coordinate force q sub j with superscript n is calculated from this equation, where xk, yk, and zk are the displacement of the case mass in the x, y, and z directions. So if you assume that x, y, and z are your generalized coordinates in a system with 3 degree of freedoms, you can easily calculate qj by using this equation. And you will see easily in the examples, without any calculations, you can predict qj. Only sometimes when we deal with the damping in our system, we will have some only one point that you should consider to calculate qj. Otherwise, it will be easily calculated from the geometry of your system, and you can predict that what is qj. And finally, the last point is, for a conservative system, qj is 0. The conservative system is a system which in that there is no external force, and also there is no damping, because in a conservative system, in fact, the energy level will be remain the same. So when the energy will be remain the same, it means that there is no damping to lose the energy, and also there is no external force to increase the level of the energy in your system. So In a conservative system, Qj is equal to 0, and you can again use the Lagrange equation to write the equation of motion for a system. Okay, we have one example, and I think we can continue this example on Wednesday. And if you don't have any question, we can wrap up this session. Okay, any question from this part so far?
Say not from this part, but say next week, which day are we having our exam?
Next week, what? Sorry.
Say next week, which day will be having our short test too?
Yes. Next week we'll have short test too, but about the date, we can discuss on Viber and obtain a suitable date for you.
Say, and the coverage will be from week 5 to week 8.
The coverage is from week 5 to week 10. In fact, the single degree of freedom system subjected to the external force or force vibration of S2F system, and also the 2 degree of freedom systems. Of course, only the free vibration of 2 degree of freedom systems will be considered in the short test too.
Okay, sir. Thank you.
You're welcome. Any other question?
No, sir. Thank you.
Okay, thank you all for your attention, and see you on Wednesday. Thank you. Bye.